Hi, today I'll be introducing my project, a novel attention calibration protocol for EEG-based BCI systems. Before we begin, what exactly is a brain-computer interface, or BCI for short? As an example, imagine we have John here, who wishes to interact with a computer directly using his mental state. He puts on this headband that can sense his brain waves. Now, what John does is that he starts to focus. When John focuses, his brainwave starts to fluctuate and change, and the headband picks this up. The headband will then transmit the signal to the computer, causing the mouse to move. Now that we understand what a BCI is, let's go through some standard components of an EEG-based BCI. Firstly, we have the EEG Sensor and Amplifier. This sensor would detect EEG signals of the user and then transmits it to the machine learning model. What the model does is then to classify the incoming EEG signal. In this case, the model will output its confidence that the EEG signal represents the user being in attention. The model then sends this confidence level to the program, which may treat each input differently. So, why do we need to calibrate the BCI? Well, imagine two users, John and Susan, trying to interact with the system. John focuses and his EEG signal is sent to the model, which classifies the signal as attention. Now, Susan focuses and sends her EEG signal to the same model. However, although both John and Susan are focusing, their EEG signature may be slightly different, which may end up confusing the model and make it wrongly classify the signal. With calibration, the model will be suited to the individual's EEG signature and will be more accurate. So, how exactly do we perform calibration? We start by creating two tasks, one for attentive state and one for inattentive state. The attentive state task might be based on some task that is known to stimulate attention. The user will then perform the task while his EEG signals are fed to the machine learning model with the attention tag. Next, the same is done for the inattentive state by sending the EEG signal tagged with the inattentive tag. Once the model receives data for both states, it will be refitted and the calibration is complete. With our understanding, let's take a look at the current attentive state calibration task. We have just seen the current attentive state task, which is called the flanker task. What exactly is wrong with the flanker task that makes it unsuitable for calibration? Firstly, the stimuli are boring, consisting only of white arrows on a black background. Next, as you saw previously, there is limited activity on the screen. Finally, the task is boring, repeating itself over and over again, with little variation. Therefore, I believe it is unsuitable for calibration. Introducing the new attentive state calibration task that my project proposes, which is based off visual search. At a glance, you can see that the stimuli are colorful and varied. Furthermore, the stimuli are all over the screen, creating a lot of on-screen activity. Finally, the design features a variable difficulty to ensure that the activity does not become stagnant. On the point of variable difficulty, let's take a detour. For every activity, it can be represented on this difficulty scale, with 0 being too easy and 10 being too difficult. An activity that is too easy will breed complacency. An activity that is too difficult will cause the user to become discouraged. Both of these scenarios are not good as they will result in lower attention levels. Therefore, we want to hit the sweet spot right in the middle where the difficulty is just right to ensure that the calibration stimulates the highest level of attention. Coming back to the new design, the variable difficulty is important to finding that sweet spot. If the program deems that the user is struggling, the number of stimuli and thus difficulty can be lowered, and vice versa for too easy. Now, let's take a look at the new design in action. Next, we compare the inattentive task. The existing inattentive task involves making the user look at the periphery of a blank screen. This is bad for two reasons. First being that it requires voluntary eye movements, which may affect the EEG signals, and second being that the user may end up focusing on the screen border. Compare that with the new design, which uses white noise and is better for the following reasons. It isn't that difficult to see which will better stimulate inattention. Now, to test the new design, I created an experiment which pitted the existing design with the new one. The experiment compared the two protocols in two aspects: subjective user feedback and objective cross-validation analysis. And the results are not surprising. In terms of subjective feedback, the new design outscored the existing design for both attentive and inattentive tasks. Hence, for subjective outcome, the new design is the winner. For objective scores, the new design outperformed the existing design with higher mean accuracy regardless of the input EEG channel settings. Hence, the new design wins again. With the new design being better than the old design on both aspects, it proves that the new design is indeed a more effective attention calibration tool for EEG-based BCI systems.